This is Related Rates 1, Day 15 of Trimester 2. The first problem is a review of implicit differentiation, so I'll go through that as I would in a classroom. So if I'm looking at the cosine of xy, I've got to use the derivative of cosine is negative sine of the argument xy, but then I need to take the derivative of that xy using the chain rule. So I've got the first times the derivative of the second plus the second times the derivative of the first. And all that's being multiplied by the sine xy. Then I'm going to rewrite this sine squared x to be sine x squared. The notation where we've got the squared up here tends to be a little bit confusing, but if I write it the way that I just rewrote it with the sine x quantity squared, I can see that it's just the rule where I bring the 2 down front, and then I've got the sine x now raised to the first power, and chain rule says that I need to multiply by the derivative of the sine x, which is cosine x. And on the other side, the derivative of the constant is 0. Tidying up, simplifying, I've got a negative. I'm going to bring this x out front. X sine xy, and the dy dx. And then distributing, I've got minus y sine xy. So that the distributive is this and that. And then still just plus 2 sine x and cosine x. So I'm trying to solve for this dy dx. The only place it shows up is right here. So I'm going to keep that term on this side of the equation, and I'm going to add this term, subtract this term. So I end up with a negative x sine xy dy dx equals y sine xy minus 2 sine x cosine x. I need to divide by everything that's not my dy dx, so I'm going to be dividing by that, and I end up with dy dx equals y sine xy minus 2 sine x cosine x all over negative x sine xy. If we wanted to not have a negative in the denominator, which is okay or not, I could multiply both the top and bottom by a negative 1. That would make this term positive and make this term negative. So I'm going to put the positive term first. I've got 2 sine x cosine x minus y sine xy all over what is now a positive sine xy. We could also use distributive and divide that and divide that, and we would end up with 2 sine x cosine x over x sine xy minus, and then the sine xy's cancel, so I would just have y over x. Any one of these three answers is fine. Now, on to the related rates. This is where we get to some cool stuff. So this is where we finally get to start applying all of this that we've been learning so far. So let's look through this problem. Suppose you have a rocket ship, and 3,000 feet away you have a camera taping the launch. After the launch, when the rocket is 4,000 feet in the air, we know that it is rising at a rate of 880 feet per second. How fast is the camera to rocket distance changing at that instant? Okay, well, we've got a couple of things that aren't changing, and we have things that are changing. So we need to keep those organized. The distance from the launch pad to where the camera is positioned is not going to change. We know that this distance from to the rocket is staying at 3,000 feet. We know that the rocket ship is headed up in the air from the launch pad. It's a reasonable assumption that that rocket's going to be going straight up, and we can say that that's a right angle. We don't know that it's a right angle, but it is a reasonable assumption for a model. At some point in time, that rocket's going to be the 4,000 feet in the air, but it doesn't stay 4,000 feet in the air. At the beginning of the problem, it's not 4,000 feet up in the air. At the beginning of the problem, it's on the launch pad. And as it takes off, at some point in time, it's 4,000 feet in the air. We also know that at that point in time, its rate of that is traveling at a rate of 880 feet per second. What we want to know is how fast is the rocket to camera distance changing. So if this is the camera down here, and the rocket at some point in time is going to be up here, I want to know how fast is that distance that I've drawn in green, how fast is that changing? Well, it's generally helpful in math, or in anything, to label what we're talking about. In math, we tend to use the variables, and I'm using x, y, and z. X for a horizontal distance, y for a vertical distance, and z for the distance between the two of them. Obviously, those can be any variables, but those will be the convention that I will be using. Okay, so on here, on this diagram, I've put all the stuff that's not going to change. That's our given at this point in time. This is our always diagram. What I'm going to look at next is what is it that I'm trying to find and when? Well, what I'm trying to find is how fast the distance to rocket, the camera to rocket distance is changing. Well, that distance is what we've labeled as z, from where the camera is to where the rocket will be is z. But I'm looking at a rate of change at some point in time. So that's going to be the change in z with respect to the change in time. I'm finding dz dt, and I'm finding that when the rocket's height off the ground, when my distance y is 4,000 feet, and the change in y with respect to t, change in time, is 880 feet per second. So I've got a drawing, and that contains the things that are always true. Those things are given, and they are not changing. Then I've got a statement of what is I'm trying to find and when. Next thing I'm going to look at is I need an equation that's going to pull together the information that I have and will include eventually what it is that I'm trying to find. So in this case, I need to make use of I want to make use of my x value, that's given. I want to make use of my y value because at some point in time I will know that the rocket is 4,000 feet off the ground. And I need an equation that's also going to contain z because I need to find dz dt. So looking at this representation that we have in the picture, I see there's a triangle, I see that it's a right triangle, and I remember back to geometry that we have the Pythagorean theorem that says that x squared plus y squared equals z squared. So that's always true of this triangle. If I take the derivative so that I can get to a dz dt, I want to know how z is changing over time. So I'm going to want to have dz dt. I get that by taking the derivative with respect to time. Using our implicit differentiation, we have 2x dx dt plus 2y dy dt equals 2z dz dt. Well, I see that I've got 2's on each side of the equation, so I'm going to divide by 2, giving me x dx dt plus y dy dt equals z dz dt. Now, it's not required that you divide by that 2, but it just makes your equation a little bit simpler, so we may as well do that. So I've got an equation that is always true, and I've taken the derivative. I've simplified my equation as well. So that I'm going to refer to that as being my always equation and its derivative. Now I'm going to talk about at this point in time. This isn't always true, but there is a moment in time when I know that y is 4,000 and the rate of change of y is 880 feet per second. Given that information, I'm going to use this equation I just came up with and see if I can find the value for dz dt. Well, I know that x is 3,000 feet. dx dt, well, how is x changing with respect to time? X isn't changing. So if x isn't changing, the rate of change is 0. The y value at this point in time is 4,000 feet, and its rate of change was given at 880 feet per second. Our z value, I don't know that. And the dz dt is what I'm trying to find. Well, in order to find this z value, I'm going to go back to our original equation, our always equation, and our always diagram, but I'm going to make it an at this point in time diagram. At this point in time, this distance is still 3,000. This distance at this point in time is 4,000. So if I want to find z, I can either use the Pythagorean theorem, or I can recognize that this is a 3, 4, 5 right triangle and get the same value as I would with the Pythagorean theorem, that z must be 5,000 feet. So that's going to come back over here as a 5,000. And now it's just time for some algebra arithmetic. So I've got this 4,000 times 880, because this is 0, divided by the 5,000 on the other side, from the other side, equals dz dt. So doing some canceling or grabbing a calculator, I come up with dz dt is equal to 704. But I need to think about units. Well, I can think about this in a couple of ways. First, just looking at dz dt, what is the unit of z? Z is the length, is a distance from the camera to the rocket, and our distances have been given in feet, so that must be feet per, and the time unit has been seconds. Well, our friends in the science department would certainly want us to justify that as well. So if we look back here, we can say, well, 4,000 was feet. The 880 was feet per second, and the 5,000 was feet. Well, if I have feet times feet per second divided by feet, I've got feet squared per second divided by feet gives me feet per second. So we agree. Oops, it's not there. It's okay. So our next problem. Assume oil is spilled from a ruptured tanker and spreads in a circular pattern whose radius increases at a rate of 2 feet per second. How fast is the area of the spill increasing when the radius of the spill is 60 feet? Okay, so using the same format I used above, first thing I'm going to want to do is draw myself a picture. So if I want to draw a picture, what shape do I need? Well, in this case, it's oil is spilled in a ruptured tanker with a circular pattern. I'm going to draw a circle. So here's my oil spill. And it has a radius R. And whose radius increases at a rate of 2 feet per second. So that the radius being a constant rate of increase, the dr dt is in my always diagram. I would again want to figure out what is it I'm trying to find and when. Well, I'm trying to find how fast is the area of the spill increasing. So I'm looking for a rate, so it must be a derivative of some kind. So it must be in the form d something dt, and the d something is how the area changes, dA dt, when the radius of the spill is 60 feet, when r equals 60 feet. So again, I need an equation. Obviously, Pythagorean theorem isn't going to help me here, so I'm not going to go back and use that same equation. But I need an equation that's going to have something to do with a circle and the area of a circle with respect to its radius. Well, going back to geometry, I know that A equals pi r squared. Nice equation, because it's going to give us the A value we need. It's got an R value. If I take the derivative, because I want to get to dA dt, I want to know how the area is changing. So I'm looking at the derivative, how A is changing with respect to change in time. And on the right-hand side, I just need to remember that pi is a constant. So if I had 3r squared, I'd have no problem taking the 3 times 2 and making it 6r. But because it's not 3, it's 3.1 and such, I've got to take 2 times the pi, and leave it in terms of pi, to the first power, and then dr dt. So that's as simplified as it can be. Then I'm going to see, well, are there some values that I can plug in here? My dA dt is what I'm trying to find. So I don't have a value to go in there. 2 pi, do I know the r? Yes, it's given as 60. And dr dt was given as 2. So my dA dt, the rate of change of the area with respect to time, is 240 pi. Again, I need units. Well, the area units would be feet squared, because our radius is measured in feet, so area is going to be in feet squared, and the change in time is the units are seconds. And again, we could say that this 60 is feet, the 2 was feet per second, so we get the feet squared per second. And that's approximately 754 square feet per second. Here and look at those boxes that I was using on the other sheet, where we start with a diagram of our always box. What is happening that's not going to change? From there, I want to come down and look at my find when, my statement of where is it I'm going and when. Then we need an equation that's going to pull all of this information together, an always equation. We'll then take the derivative. Then we'll look at this moment in time, our when. Plug in the values we have. If there's a value that we don't know, we might need to come over and do a little bit of side work with the at this moment diagram and solve for a missing piece, bring that back over, solve, and then we need to remember to put our units on there. So I hope that this has been helpful, and good luck.